I'm a computational linguist. In the course of our research, we make a lot of figures and graphics to explain our research. And some of our research is on grammars. So all of that comes together today when we talk about the grammar of graphics, my preferred way of creating graphics. Because many of you know the linguistic definition of a grammar, you know that a grammar is a recursive definition of rules that defines a means of communication, where non-terminals transform into some collection of other non-terminals and terminals. Now, technically, the grammar of graphics isn't a grammar in this sense. It's not recursive, it doesn't have non-terminals, and so on. But it is about communication and transformations. The grammar of graphics was developed by Lee Wilkinson, who died recently in December 2021. In a tribute to him, Jessica Holman summed up his contributions in the field. And her tribute captures two of the ways that the grammar of graphics line up with the ways that linguists think about grammars: equivalence through transformations and grammaticality. The first relationship between how we think of grammars and the grammar of graphics I'd like to highlight is that grammars allow for transformation. Say you have the sentence, "The ball hit Mary," and you'd like to turn that into a question that asks, whom did the ball hit? In some sense, this is the same underlying sentence, but it's ordered differently. In many languages, you have WH movement to put question words first, and the verb itself has changed. But the underlying idea is the same. Somebody's getting hit. The same holds true for graphs. Even though the pixels of these two charts are very different, the underlying data are the same. The elegance of the grammar of graphics is that this change between the two forms of this presentation is merely an aesthetics module or layer of the colors and the elements and the coordinate system that the plot is using. But the underlying data are the same. And for someone making a plot, this is important. You might need to explore lots of different transformations and presentations to understand what the heck is going on with your data, or to figure out the right way to communicate it. The grammar of graphics makes this easy. The flip side of what a grammar allows is what it doesn't allow you to do. In language, such a disallowed verboten sentence is called not licensed or ungrammatical. It's not a valid sentence. So you can't say things like, "hit ball Mary the." Similarly, one of Lee Wilkinson's insights is that a lot of mistakes in visualization data were a deviation from the grammar of graphics. Doing a transformation at the wrong time or applying statistics inconsistently. You go in this order, or you don't go at all. For those who are new to the grammar of graphics, this can be frustrating. You want to do something. You need to figure out what stage of the grammar it would lie at, what the commands are, and how it interacts with the other transformations. Why is it so complicated? Part of the complication keeps you on the straight and narrow. Other plotting packages give you access to raw pixels or vectors. It's easy to do anything you want, but it's also easy to make bad plots. We'll talk more about that in a little bit. In the next video, I'll talk about the sequence of creating graphics. As I go through those steps, keep this figure in mind as we build up visualizations in implementations of the grammar of graphics like ggplot2 and plot9. And this is why I recommend learning the grammar of graphics. Just like natural language, it's about communication. And good communication requires structure and rules. If you play by the rules, you'll get your point across. And using some of the packages we'll talk about, you'll look good while doing it. This is just a single lecture from a course. YouTube likes to show you these videos out of order, but if you go to the course webpage linked below, you can see the lectures in the right order, and you can get resources like homeworks or suggested reading. You can also visit quanta.org if you want to learn about our systems for creating computers that can answer questions, where Quanta stands for question answering is not a trivial activity. If you want to help the channel, provide a big gradient to the algorithm by liking and subscribing.